In question number 9, a uniform electric field exists in a region. A charged particle having charge minus q and mass m enters at point A with velocity v naught j cap. It moves through the electric field and exits at point B with velocity given by this expression. Then we have to check the validity of given options. So first of all, let's analyze the situation. The negative charge particle enters through this point and it gains a velocity in x direction. It means that the electric field is acting in this direction, next direction, due to which it gets acceleration in this direction. And if I see the motion in vertical direction, then its velocity reduces in magnitude. It means that the electric field in y direction is acting in this direction, and acceleration due to this electric field will act in this direction. Now, if I write the work done by electric field is equal to loss in its kinetic energy in the y direction, then it is equal to Q into EY into magnitude of displacement is A, that is equal to loss in its kinetic energy in y direction can be written as half m into v naught square minus half m into v naught by 2 whole square. At the exit point, the direction of vertical velocity is in this sense, and let x I have taken positive, x direction velocity is in this sense. So if I solve this, the value of EY comes out to be 3m v naught square divided by 8qa. So we have find out the value of EY. Now we have to find out what is the value of EX and what is the final velocity in x direction. So in order to calculate this, I am writing the equation in x direction. So the force acting on the particle in x direction is Q into Ex, and that is equal to mass into acceleration in x direction. Further, since the acceleration is constant in x direction, so I can apply Vx or x. Let I am saying this x as my Vx, that is the final velocity in x direction, is equal to initial velocity in x direction is 0 as the particle is projected along j cap, plus the acceleration in x direction is Ax, which I can write as Q into Ex by m into time t. Now I have to calculate what is the time taken by the particle to reach from A to B. So in order to calculate the time, I have to go to the vertical direction motion. So the vertical direction motion, if I calculate, the final velocity is minus v naught by 2 in y direction. Initial velocity is v naught. Acceleration in y direction can be calculated as q into Ey. I have find out the value of Ey, that is 3m v naught square divided by 8qa, that is equal to mass into acceleration in y direction. So the acceleration in y direction comes out to be 3 v naught square upon 8 into a. So if I write with sign, this can be written as minus 3 v naught square by 8a into t. So on further solving, the value of t comes out to be 4a divided by v naught. So if I substitute the value of t here, it comes out to be q into Ex by m into t, that is 4a divided by v naught. Now we know that the work done by electric field in x direction, that is q into Ex into displacement in x direction is a, that is equal to change in kinetic energy of the particle in x direction, that can be written as half into m into Vx square minus 0. So if I see here, q into Ex into a is equal to half into m into Vx square. So I can replace this thing by half m into Vx square. So on substituting this and solving, we get the value of Vx is equal to v naught by 2. So option C is correct and D is wrong. Now if I substitute the value of Vx here, I get the value of Ex, and the value of Ex comes out to be m v naught square divided by 8q into a. So we can see that the option A is correct and B is wrong. So the correct answer for question number 9 are option A and C. Let's move to question number 10. In question number 10, consider the shown infinite network. Potential difference 12 volt is applied between points A and B as shown in figure. Then we have to check the validity of given options. So in this question, if I leave this first unit and find out the resistance of this infinite series, then it comes out to be 2 ohm. So in that case, if I make this arrangement in this way, this is 1 ohm, this is 2 ohm, and this infinite series resistance is 2 ohm, then this is my point A and this is my point B. Now the equivalent of these 2 ohms is 1 ohm, and 1 ohm and 1 ohm is in series, then it is 2 ohm. So we can say that if 12 volt potential difference is applied between these 2 points, then 6 volt potential difference will come across these 2 points, and 6 volt potential difference will come across these 2 points, that is R and S. Now this 6 volt potential difference is further divided when I make this arrangement. So this point is P and this point is Q and this point is S, this point is R. Then this 6 volt is further divided as this as 3 volt and this as 3 volt and so on. So if I see, the potential difference between R and S is 6 volt and the potential difference between P and Q is 3 volt. So let's check the options. So option C is wrong and option A is correct. Now we have to find out what is the value of I2 and I1. So I2 is the current in this branch, then I2 can be written as potential difference 12 volt divided by total resistance. So the total resistance comes out to be 2 ohm. So it comes out to be 6 ampere. So option B is correct. And if I calculate the value of I1, then I1 can be written as the potential difference in this branch RS is 6 and the resistance is 2. So it comes out to be 3 ampere. So option D is also correct. So the correct answer for question number 10 are option A, B and D. Let's move to question number 11. In question number 11, consider a uniform rigid square wireframe ABCD of mass 4m and side length L placed in an external uniform magnetic field B0 in XY plane at an angle theta from axis as shown. If at t equal to 0, current I0 starts flowing in the wireframe, and due to this current, torque experienced by the wireframes comes out to be I0 L square B0 into minus I cap by root 2 plus j cap by root 2, and its angular acceleration at that instant is alpha, then we have to check the validity of given options. So if I write the uniform magnetic field in vector form, that can be written as B vector is equal to B0 into cos theta I cap plus sin theta j cap. And if I0 current is flowing in this wireframe, then the magnetic moment of this current carrying loop can be written as I0 into area, that is L square into K cap. So if I take the cross product, then torque vector can be given by M cross B, and it is equal to I0 into B0 into L square into sin theta minus I cap plus cos theta into j cap. So if I compare with the given expression of the torque, then the value of theta comes out to be 45 degree. So option A is correct and C is wrong. Now we have to find out what is the value of alpha. So in order to calculate the value of alpha, so we have to check along which direction this loop is rotating. So if I see, this is the direction along which the torque is coming. So we have to write the moment of inertia of this system about this axis. So in order to calculate this, I have to find out what is the I about this direction. So let the Ix of this given arrangement in this direction is Ix. Then the value of Ix can be written as the moment of inertia of this rod about this axis is ml square by 12, and this rod is also have the same moment of inertia. So 2 times m into L square by 12 plus the each element of this rod is at a distance of L by 2 from this axis. So we can write 2 times m into L by 2 whole square. So if I solve this, it comes out to be 2 by 3 ml square. Same moment of inertia will come along this direction. Then the Iz about this axis can be written as Ix plus Iy, which is also equal to the moment of inertia about this axis plus this axis. So if the moment of inertia about this is I, then I can say that this is also equal to I. Now the writing torque equation about this line, I can say torque about this line is I naught into L square into B naught, that is equal to I 2 by 3 ml square into alpha. So on solving, the value of alpha comes out to be 3 by 2 into I naught B naught divided by M. So option B is the correct answer. In option D, net magnetic force on the wire frame will be 0. So when the wire frame is kept in a uniform magnetic field, the magnetic force experienced by the magnetic field is always 0 irrespective of the orientation of magnet. So option D is also correct. So the correct answer for question number 11 are option A, B and D. Let's move to question number 12. Question number 12, binding energy per nucleon versus mass number curve for nuclei is shown in figure A, B, C and D are 4 nuclei indicated on the curve. The processes that would release energy is R. So if I calculate, then binding energy of A is equal to 120 into 7.5. So it comes out to be 900 mega electron volt. Similarly, if I calculate the binding energy of B, then it comes out to be 720 mega electron volt. Binding energy of C comes out to be 510 mega electron volt, and binding energy of D nuclei comes out to be 150 mega electron volt. Now, if the binding energy of the daughter nuclei are more than the reactant, then the process would release energy. So, in option A only, the binding energy of daughter nuclei is more than the reactant. So, the correct answer for question number 12 is option A. Let's move to question number 13. In question number 13, a superconducting ring of radius A and inductance L is in a uniform magnetic field B naught and current in the ring is equal to 0. The ring is turned to the position perpendicular to vector B naught. At final situation, we have to check the validity of given options. So suppose initially this is a ring and the uniform magnetic field lies in this direction and its value is B naught. So at this moment, the flux through the ring is 0. Suddenly, the ring is made perpendicular to the magnetic field B naught. So when suddenly the ring is turned by an angle of 90 degree, then the flux through the ring must be equal to 0 because the ring is conducting in nature. So it is the property of the inductor to maintain the flux immediately after the change. So in order to maintain that flux, the induced current will come in the ring. Let I is the induced current, and the flux through this induced current balances the flux due to the external uniform magnetic field. So I can say that L is the inductance, then L into I must be equal to magnetic flux due to magnetic field B naught. So B naught into pi into A square. So from here the value of induced current through the ring comes out to be B naught into pi A square by L. So option B is correct and A is wrong. Now we have to check the validity of option C and D. Now in option D, flux through ring does not change upon its rotation. So immediately after the change, the inductor coil will maintain its flux. So option D is also true. Now we have to check the validity of option C. So due to this induced current, let the magnetic field at the center of the ring is B1. So the net magnetic field at the center is given by B naught minus B1. The value of B1 can be calculated as mu naught I by 2R. So mu naught divided by 2 into R into I, and the value of I is B naught pi into A square by L. So if I solve this, it comes out to be mu naught B naught pi into A divided by 2L. So if I substitute the value of B1 here, then it comes out to be B naught common 1 minus mu naught pi A divided by 2L. So option C is also correct. So the correct answer for question number 13 are option B, C and D. Let's move to question number 14. In question number 14, figure shows a system of two large metallic plates carrying current in opposite direction. The current in unit length delta L of plate is given by I is equal to J into delta L, means the current per unit length is J. If BP and BQ are the magnetic field induction at points P and Q respectively, then choose the correct options. So we know that suppose if there is a sheet and the current is coming out of the sheet and its linear current density is J, then the magnetic field at some distance is given by, due to this infinite sheet, is in this direction if the current is coming outside, and the magnetic field value is given by mu naught into J by 2. So if I use this result, the magnetic field due to this sheet at point P and Q is in this direction, and it is equal to mu naught into J by 2. Now if I consider this sheet, the current in this sheet is going inward, so the direction of the magnetic field due to this at point P is in this direction and at point Q is in this direction. So the magnetic field at point P gets cancelled out and the resultant value of the magnetic field at point P becomes 0, while the magnetic field at point Q gets added, so it is equal to 2 times mu naught J by 2, so it comes out to be mu naught into J. So options A and B are the correct options. So the correct answer for question number 14 are option A and B. Let's move to question number 15. In question number 15, in the arrangement shown in the figure, the point source S oscillates about point O along central axis in a small amplitude. The fringes are formed on the screen. So when this source is oscillating along this direction, then the path difference at any point on the axis comes out to be x d by d, which is same irrespective of the position of the source along this axis. So if the path difference is same, then the fringe width also remains same. So option C is correct and A and B are wrong. In option D, number of fringes on the screen increases when S moves away from the slits. The number of fringes on the screen will remain same and the pattern will remain same. So option D is wrong. So the correct answer for question number 15 is option C. Let's move to question number 16. In question number 16, a point object O is placed in between two large plane mirrors M1 and M2 whose reflecting surfaces makes an angle 30 degrees with each other. If N1 and N2 are the number of images formed by M1 and M2 respectively, then choose the correct options. So in order to solve this problem, I have to make a table. This is the mirror M1 and this is the mirror M2. The first image formed by mirror M1 is at an angle of 20 degrees. Then M2 makes of this image which is at an angle of 50 degrees. Then M1 makes the image of this image which is at an angle of 80 degrees from M1. Then M2, it is at an angle of 110 degrees. For M1, it is at an angle of 140 degrees. And then for M2, it is at an angle of 170 degrees. Now, if the first image is formed by the mirror M2, then it is at an angle of 10 degrees. Then M1 forms the image of this image at an angle of 40 degrees. Then M2 forms the image at an angle of 70 degrees. Then M1 forms the image at an angle of 100 degrees. Then M2 forms an image at an angle of 130 degrees. And finally M2 forms the image at an angle of 160 degrees. So after this, the angle exceeds 180 degrees. So if we calculate, then the number of images formed by mirror M1 is 6 and by mirror M2 is also 6, and we can see that these images are coinciding in nature. So option A and B are the correct answer. Let's move to question number 17. In question number 17, a particle is projected from point P with a speed v, which is minimum possible speed to just pass through the smooth fixed hemisphere of radius r. Choose the correct options. Q is the point where particle land on horizontal surface. Suppose the particle is projected from here, from the top of the hemisphere with a negligible speed, that is 0 speed, then it moves on the smooth hemisphere, and at this point it loses contact with the hemisphere, and suppose it lands on the point Q on the ground. So if I calculate the speed with which it strikes the ground, then I can say that mgr is equal to half into m into v square. So the value of v comes out to be under root of 2gr. Suppose I reverse the process. I throw a particle from Q with a speed v such that it just reaches to the top of the hemisphere with the negligible speed. In this situation, it will crosses the hemisphere and it reaches to the point P. So in that case, we can say that if it is projected from here with the speed v, then the value of v is equal to under root of 2gr. So option A is correct and B is wrong. Now the value of this radius is r. So from this diagram we can say that the value of AQ is greater than r. So option C is also correct. So the correct answer for question number 17 are option A and C. Let's move to question number 18. In question number 18, a semicircular ring of radius r is rotating about its one end O with angular velocity omega. Uniform magnetic field B0 exists perpendicular to the plane of ring. Then potential difference. So if I calculate potential difference about point O and A, then this is the effective length, and the effective length is root 2r. This is the sense of rotation, and the magnetic field is inward. So the point A is at higher potential. So VA minus VO can be written as B omega L square by 2. So B0 omega, the value of L effective is root 2r whole square by 2. So it comes out to be B0 omega r square. So option B is correct. Now similarly, if I calculate the potential difference between point O and B, then B is at higher potential. So we can write VO minus VB is equal to minus B0 omega. L effective value is 2r. So 2r square divided by 2. So on solving, it comes out to be minus 2 times B0 omega r square. And if I calculate VA minus VB, then it can be written as VA minus VO plus VO minus VB. So on substituting this value, we will get the final answer, that is minus B0 omega into r square. So we can say that option A, B and C are the correct options for question number 18. Let's move to question number 19.